Hello, Chem 1A. This is Chapter 12, Lecture Video 2, and in this lecture video, we're going to talk about the different types of intermolecular forces. Intermolecular forces, often we kind of abbreviate this whole thing as IMF for intermolecular forces. So if you see IMF in any of our assignments or our lecture videos, that's what I'm talking about. I'm talking about intermolecular forces. Now, we can really break up the different types of intermolecular forces into two groups. One for neutral atoms and molecules, where we have London dispersion, dipole-dipole, and hydrogen bonding. And then with ions, which is the ion-dipole interaction. And these are the ones we're going to be covering in this lecture video. Now, these three often are collectively called the van der Waals forces. And we've actually seen this name before when we talked about the real gas law equation, right? The whole P plus A N over V squared times V minus Bn is equal to nRT, right? This equation is called the van der Waals equation. The reason why it's called that is because we're taking into account these three intermolecular forces that we assume gases don't have, but in reality they do. So that's part of what this gas law was taking into account, and that's why it's called the van der Waals forces for these types of intermolecular forces. So London dispersion forces, they exist between all molecules and atoms. So one of the things you're going to be asked to be doing for questions in this chapter is determine what intermolecular forces are present. And one answer to that question is always London dispersion. London dispersion is always present, no matter which molecule we're talking about, or atom, or compound, whatever, they all have a London dispersion interaction. It's also the weakest type of intermolecular force. And what is London dispersion? Well, it's a function of what we call the molecular polarizability. Now, with all molecules, they have electrons present. And these electrons aren't static. They're not stationary. They're not sitting still. They're constantly moving around. And when we talk about polarizability, what we're really saying is that there's the possibility for what we call temporary dipole moments. And temporary dipole moments are where, for an instant, there might be more electrons in one part of the molecule versus the other part, creating a gradient of charge, which is what we know is a dipole moment from chapter 9 and 10. And this is what we mean by molecular polarizability. Those temporary dipole moments create attractions and repulsions between molecules. We're effectively, what we say, distorting the electron cloud of the molecule. The larger the molecule, the more electrons, and therefore the easier it is to polarize that molecule temporarily. What this means is the London dispersion force increases in strength with increasing molar mass or molecular weight, like I kind of hinted at in an earlier slide. So what I need you to take away here is London dispersion force is present in anything. If you're ever asked what intermolecular forces are present, one of those will be London dispersion. And two, it's due to molecular polarizability, in other words, the formation of temporary dipole moments. And three, its strength increases with increasing molar mass or molecular weight. And these are the three things I need you to know about London dispersion forces. Also, sorry, the fourth would be that London dispersion are the weakest type. Dipole-dipole interaction is a little bit stronger than London dispersions, actually quite a bit stronger than London dispersion. Dipole-dipole forces bind molecules together when the two molecules have permanent dipole moments. Now, when you have a permanent dipole moment, you're a polar molecule. Now, polar molecules, they always have a permanent dipole moment. That's what we learned about in chapter 9 and 10. And so you can only have a dipole-dipole interaction when the molecule is polar. And so if you can't figure out whether a molecule is nonpolar or polar in this chapter, it's going to be a big handicap, because the polar molecules are only they're nonpolar molecules won't have dipole-dipole, whereas polar molecules will. And if you can't tell between the two, then you're not going to be able to tell if dipole-dipole interaction is present or not. But it's very straightforward interaction. In a polar molecule, we have one side of our molecule as partial positive, right? So this guy's on this partial positive side. And we have one side of the molecule that's partial negative. And if we have this, partial positive charge here and this partial negative charge here, there's going to be attractions between these two sides of two separate molecules, creating this dipole-dipole interaction. All right. Hydrogen bonding, which is the second to last intermolecular force we're going to talk about, is kind of like a souped up dipole-dipole interaction. It's a dipole-dipole interaction on steroids, if you will. It's much, much stronger, but it's very similar in concept, right? We have a partial positive, this time on our hydrogen atom. And that hydrogen atom is connected to another element via a covalent bond. This bond must be very polar. And since it has to be very polar, the possible elements for X and Y here are nitrogen, oxygen, or fluorine. Those are the only possible elements you can have to still have a hydrogen bonding interaction. Now they have to have hydrogen directly attached to them via covalent bond. And that's the only time you're going to get any hydrogen bonds present, right? So for instance, if we had like CH3F, this actually, we have fluorine and hydrogen both present in the compound, which makes you think maybe hydrogen bonding. But actually, if you draw the Lewis structure of this molecule, it's like this. There is no hydrogen attached to the fluorine, and therefore there is no hydrogen bonding in this molecule. Whereas if you have like something like this in ethanol, for instance, we have a hydrogen directly bonded to the oxygen. We can have hydrogen bonding here. Cool. So this is the strongest of the main three types of intermolecular forces, which are the last three that I just covered. Hydrogen bonding is the strongest. Then we have dipole-dipole, which is slightly weaker than hydrogen bonding. And then the weakest type of the main three is London dispersion, whose strength can increase with molar mass. So let's talk about the very last type of intermolecular force that we're going to discuss, which is ion dipole. This one's kind of very specialized because it only happens when we have a polar molecule with a ion in a mixture. So it only can happen with a mixture. The most common occurrence is when we dissolve an ionic compound in water, because water is a polar molecule. And if I dissolve an ionic compound in water, I get the ions separating up into the positive and negative charges. And then we have ions present with a polar molecule, in this case, water. Water has a permanent dipole moment, and this polar nature creates ion dipole interactions between the ions and the water. In fact, ions in water don't hang out alone. They typically hang out with, as you can see here, 6 molecules of water attached to them. Now, one of the things you might notice is that the positive charged one, all the oxygens are facing the positive charge. And that's because on water, we have a partial negative charge on the oxygen and a partial positive charge on the hydrogen. So opposite charges attract with this partial negative charge on the oxygen attracting to the positive charge on the ion. The opposite is true of the negatively charged ion, right? All the hydrogens are facing the negatively charged thing for water. And this again is for the same reason, right? We have this negative charge on our ion, and on the water, on the hydrogen side, we have the partial positive charges that are attracting to the negative charge. Any compound that's polar can experience ion dipole as long as we mix that polar molecule with an ion. So if we have polar molecules and ions present in our mixture, then we have ion dipole interaction occurring. Most often, however, this occurs in aqueous solutions where we dissolved an ionic compound, though.